Hello and welcome back to Edu-Malanga. Today we are continuing with the sum of geometric series. We will be doing examples on this topic. The sum of geometric series is topic number 4 in the first unit of the year, which is patterns, sequences and series. We will do 2 examples today. And the first example that we will look at under the sum of geometric series is determine the sum of the first 5 terms of this geometric series. If you're joining us for the first time, you may not be able to understand geometric series very well. I will suggest that you go back and you watch the previous video which we made on geometric series. We introduced them and we derived a formula for summing n number of terms of a geometric series. So if you're unable to understand what we're doing here today, I suggest you go back and watch that video. Let's get started solving this example. What we will do first is to remind ourselves of the 2 formulas that we came up with in the previous video for summing n terms of a geometric series. Let's remind ourselves of the formulas. The formulas look like this. You have Sn, which is the sum of n terms of a geometric series, is equal to A, that is the first or the starting term of the series, times r to the power of n. R is the common ratio for a geometric series, and n is again the number of terms, minus 1, close brackets, divided by r minus 1. Or you have A times 1 minus r to the power of n, close brackets, divided by 1 minus r. These 2 formulae are both correct and easier to use under different circumstances. The first formula is easy to use when you have r greater than 1 or less than 1. So for example, if your r is a number such as equal to 3, then you're going to have 3 to the power of something minus 1. It's easier to use this formula. And if your r is a fraction, so negative 1 is less than r, which is also less than 1. If your r is a fraction, which is a number that will fall in between here, then it's easier to use this formula because you're going to have 1 minus a fraction, and then it becomes easy for you to solve. I hope you're still with me. So we're going to use one of these 2 formulae to solve example number 1. We will start by writing down what we've been given in the example. Then we will solve the question. So we've been asked to determine the sum of the first 5 terms. So what we're given, the first thing we'll see is that n is equal to 5. N is the number of terms that we're summing, and in this example we've been chosen to do 5 of them. Now that we've determined n, the formula also needs us to have a and r. So we're going to come back to the example. We can simply read a off here. A is equal to 2. We can write that A is equal to 2. And to find R, what we need to do is to divide 2 terms that follow each other. We're going to use term 2 and term 1. So our R is equal to term 2 divided by term 1, which is going to be 12 divided by 2, and that's equal to 6. So since we found that our R is equal to 6, we can come back to these 2 formulae that we derived over here. Our r is greater than 1, so it's easier for us to use the first one. We're going to substitute everything that we have over here into this formula, and we're going to solve for the sum of the first 5 terms of the geometric series. Let's rewrite the formula again. Sn is equal to A times open brackets r to the power of n minus 1, close our brackets, divided by r minus 1. And let's substitute in. We're going to have S5, our n is equal to 5, is equal to, our a was 2 and our r was 6. Let's write down 2 times open brackets, 6 to the power of 5 minus 1, close brackets, all over 6 minus 1. We're going to use our calculators and enter this expression and then divide it by 6 minus 1. What we're going to get is that S5 is equal to, the numerator is going to equal to 15,550, and in the denominator we're going to have 6 minus 1, which is equal to 5, and when you simplify this expression, it's equal to 3,110. So the sum of the first 5 terms of this geometric series is equal to 3,110. I hope you were able to follow the solution that we did over here. We're going to move on now to example 2. Example 2 is sum these terms of a geometric series, and the terms we have start from the number 4 and they go on all the way to the number 26,244. So what we will see with this geometric series is we haven't been given what n is. We can easily find a, we just read it off here. A, let me write it down. A is equal to 4, and we can also very easily find r by saying r is equal to term 2 divided by term 1. That would equal to 12 divided by 4, so that would be 3. But our n, we haven't been given. We don't know what it is. So we will have to use the last term that we're given over here, solve for n, and we will be able to substitute into the equation and solve for the sum of these terms of the geometric series. I hope you're still following. Let's start then by solving for n. To solve for n, we're going to use the formula for a geometric sequence, and the formula looks like this. We have Tn is equal to a times r, yes, to the power of n minus 1. Okay, we do have a and we do have r, and we also have Tn because that's the last term over here, 26,244. So we can substitute everything into that equation, then solve for n. Let's get started. So Tn is equal to 26,244 is equal to 4, which was our a, times 3, which was our r, to the power of n minus 1. We'll first divide by 4 on both sides of the equation. Divide by 4 over here, divide by 4 over here as well. The 4's will cancel out on this side, and on this side when you say 26,244 divided by 4, the answer is 6,561 is equal to 3 to the power of n minus 1. It's a bit tricky to solve for n. We know that the base number we're going to use is 3. So what we do is we use an iterative process. Iterative means you keep changing the number. So we're going to do 3 and we're going to just pick randomly to the power of 6, 3 to the power of 7, 3 to the power of 8, and we're going to keep going up until we find 3 to the power of something that is equal to 6,561. We're going to use our calculators to do this again, so let's get started. 3 to the power of 6 is equal to 729, and 3 to the power of 7 is equal to 2,187. 3 to the power of 8 is equal to 6,561. So 3 to the power of 8 is equal to 6,561. Let me rewrite the expressions together. We're going to have 6,561 is equal to 3 to the power of 8, which is equal to 3 to the power of n minus 1. Now let's look at the powers. We have 3 to the power of 8 and 3 to the power of n minus 1. We are trying to solve for n. We have the same base on both numbers, so that means the powers can be equated as well. So what we will then do is we will say that 8 is equal to n minus 1. So therefore, if we add 1 on this side and 1 on that side of the equations, the negative 1 will cancel out, and we're going to have that n is equal to 9. So we've now solved for n. Can come back to all the things we were given. N is equal to 9. We now have everything that we need to substitute into the formula which would be this one again, and solve for 9 terms of the geometric series that we are given over here. Let's get started doing that. We'll rewrite the formula. We have Sn is equal to a times open brackets r to the power of n minus 1 close brackets divided by r minus 1. That's going to equal to, when we substitute everything, S9, because we have 9 terms, is equal to, let's remind ourselves what everything is. A is equal to 4 and r is equal to 3. So we're going to have 4 times open brackets 3 to the power of 9 minus 1 close brackets, all divided by 3 minus 1. Again, we're going to put this into our calculator. We're going to have S9 is equal to, in the numerator, the number will be 78,728, and in the denominator, we're going to have 2. And so in the end, 9 terms of the geometric series that we're adding equals 39,364. And that is the solution for example number 2, where we were asked to sum the terms that were given for the geometric series. I hope you were able to follow the examples that we did today. We're going to do one more video with examples on the sum of geometric series before we move on with the topic. I hope you will be able to join us for that one as well.